let's move on to problem 5. Problem 5 goes as follows. One of the angles of a rhombus. Now a rhombus is a quadrilateral that is a parallelogram and all the sides are equal. So in this rhombus, all the sides have side length 2 and the angle indicated is 30 degrees. Our job is to calculate the area and to demonstrate that there are lots of ways of solving a lot of problems. I'm going to solve this problem in 2 ways. Alright, so let's have a look at solution 1. Solution 1, I'm going to solve this using pure geometry. So nothing crazy but just geometry. But to solve it, what I'm going to do is I'm going to have a magic construction. Okay, so here I have my parallelogram. So that's 2 units and that's 30 degrees and that's 2 units. And the idea here is we are interested in needing the vertical height if you're using the base AD. So let's drop a perpendicular height and let's even extend the perpendicular height so that we get to the stage where this is the midpoint as indicated. So what we have is the following. It's a perpendicular height, so that's 90 degrees. And if that's 30 degrees, the angles have to add up to 180. So let's do a little bit of accounting. What plus 30 plus 90 gives me 180? Yes, the answer is 60 degrees. Good. Now, by symmetry, we can see the triangle at the top and the triangle at the bottom are congruent. So that is 30 degrees and that's 60 degrees. Now, let's have a look at triangle ABE. Triangle ABE is an isosceles triangle. Why? Because all the angles are 60 degrees. Angle A, angle B, angle E is 60 degrees. So it is an equilateral triangle. And knowing that AB is 2 units, that means that AE is 2 units. And because this is the midpoint, we know that that is 1 unit. And we know the distance from there to there is also 1 unit. So with this magic construction, we are now in a position that knowing that ABCD is a rhombus, we know it's a parallelogram. But more than that, we now know that we have the base, AD, and we have the vertical height from the properties of ABE being an equilateral triangle. So now we get to use theorem 1. And theorem 1 says that the area of parallelogram ABCD is base times height. So in this case, the base is AD, which is 2 units, and the height is 1. And 2 times 1 is 2. And that is the answer to this problem using the area of a parallelogram and a magic construction. There is a second solution if you know trigonometry. If you know trigonometry, we can say that the area of parallelogram ABCD is going to be twice the area of triangle ABD. Because if you connect B to D, you can see that the triangle on the left and the triangle on the right has the same area because they are congruent. Great. And there's a theorem that says that if you have a triangle and you have 2 consecutive sides and the angle between them, there is a formula for its area. So you can look it up on the internet or in a textbook, but for now, just believe me that the area of triangle ABD, it is AB times AD times the sine of the angle between the 2 sides. So this is sine ABAD. Great. So here we have 2 times AB, which is 2 units, AD, which is 2 units, times sine of BAD, which is sine 30 degrees. And if you've done a little bit of trigonometry, you would know that sine 30 degrees is a half. So what we have is 2 times 2 times 2 times a half, which also evaluates to let me just have a pick here. So, oh sorry, it's a half. So the area of triangle ABD is a half AB AD sine 30 degrees. So I've forgot the other half lurking over here. So in essence, what you have is 2 times a half, which is 1, 2 times a half, which is 1. So it also evaluates to 2. So the area of a triangle using trigonometry is a half multiplying the two sides times the sine of the angle between them. So oopsie daisy for that. But you see, if you properly apply that alternative formula, knowing two sides and the angle between the two sides, you see in both cases you get an answer of 2. Between the two solutions, I like solution 1 a little bit more. Great. All right. So 5 problems down. Let's have a look at problem 6. So first, let's read the problem. Find the shortest distance from the origin to the straight line having equation 4x plus 3y equal to 60 degrees. So for this problem, let's first try to understand the problem. So our first task is to draw the straight line 4x plus 3y equal to 60. Now to draw a straight line, you need 2 points on it. Any 2 points will do, but let's be smart about it. Let's first off calculate the x-intercept. How do we calculate the x-intercept? Yes, to calculate the x-intercept, we let y equal to 0. So what we have is 4x plus 3 times 0 is equal to 60. So we see that x is 60 divided by 4. To divide by 4, you halve twice. So half of 60 is 30 and half of 30 is 15. So 60 divided by 4 is 15. And now let's calculate the y-intercept. So the y-intercept, we let x equal to 0. So this time around, 4 times 0, which is 0, plus 3y is equal to 60. So y is 60 divided by 3. Again, you don't need a calculator to do this calculation, because 6 divided by 3 is 2. 60 divided by 3 is 20. And now we can draw this diagram. So Cartesian plane, that's the x-axis, that's the y-axis, and what we have is our little diagram over here, and it cuts the x-axis at 15, so we know that that distance is 15, and we know it cuts the y-axis at 20, so we know that that distance is 20. And we have this line, let's say it passes through points D and E. So we calculated where it cuts the x-axis, that's point D. Where it cuts the y-axis, that's point E. All right. Now, the origin is where the x-axis and the y-axis intersect. And we need to calculate the shortest distance from the origin to the straight line. So imagine that this line is water. And you're at point O, and you are thirsty. So what you want to do is get to the water as quick as possible. So you are going to try to find the point on that straight line with equation 4x plus 3y equal to 60, where you have to do the least amount of walking because you are thirsty. And playing with properties of right angle triangles, you know, in a right angle triangle, the longest side is the hypotenuse. It's not hard to see that the point that you're looking for is point F, where OF is perpendicular to DE. So to find the shortest distance in this problem evaluates to finding the length of OF. OF being such that point F is on line segment DE, so that OF is perpendicular to DE. You can clearly see if you pick any other point, let's say you pick that point over there, let's call it F dash, that the distance from O to F dash is more than O to F, because in a right angle triangle the hypotenuse is the long side. So it boils down to calculating the distance from O to F. Alright, now we got to do that mathematics. Now, do we have enough data to work it out? Well, we know that OED is right angled. So it means that we can calculate DE using Pythagoras. So calculating DE using Pythagoras, you can do it the long way. One way you can notice is that it is a multiple of the 3, 4, 5 triangle. You take the 3, 4, 5 triangle and you multiply it by 5 units. 3 times 5 is 15. 4 times 5 is 20. 5 times 5 is 25. So DE will be 25 units by scaling up the 3, 4, 5 triangle. Or you can do it the long way by saying DE squared is OE squared plus OD squared. Doing the maths, you will also agree that using the theorem of Pythagoras, that DE is 25 units. All right, now we have DE. Does that help us to calculate OF? And it does. Using the philosophy of calculating something in two ways, let's calculate the area of triangle OED in two ways. One way we can do this is by saying, okay, it's going to be a half OD times OE. Or it is going to be a half using the base DE. What will be the vertical height? Yes, you see it quite clearly from the diagram. That's OF, and that's precisely what we are looking for. Great. Now let's fill in. So a half OD, which is 15 units, times OE, which is 20 units, should be a half DE. DE, we need it, and we did that using the theorem of Pythagoras, which is 25 times OF. So the halves cancels, and what remains is that OF has got to be 15 times 20 over 25. I'm going to rewrite as 5 times 5. Why do I do that? Because 15 divided by 5 turns into 3. 20 divided by 5 turns into 4. So OF is 3 times 4, which is 12 units. And that is the answer to this problem. Again, there are other ways you could have solved this problem, but using areas, we get to calculate the area in two ways, and from that we get the distance from O to F, which is the shortest possible distance, starting at point O, going to this line that passes through points D and E. Good. That is problem 6, done and dusted. Alrighty, let's see what problem 7 entails. 6 circles, each with radius 2, are arranged in 2 rows of 3. They touch each other, enclosing the region shown. Find the area of this cute little funny quirky region. Alright, so again, let's first try to understand the problem. And my philosophy is whenever you're dealing with circles, it's good to indicate the center of the circle. So clearly, this is the center of that circle, this is the center of that circle, and this is the center of that circle. Looking at this circle, that's its center, that's the center of that one, and that's the center of that one. Now what we can do is we can connect the centers, and we have this little diagram that pops up like this. All right, now I'm going to connect that to there, and we have that, and that. All right, now it's important that you read the question. 6 circles each have radius 2, okay? So you can clearly see we have 1, 2, 3, 4, 5, 6 circles. They each have radius 2. Now, again, to make my life easy, I am going to introduce variables. So let's say the area of that quarter circle is A. And because each of the 6 circles have the same radius, that quarter circle is A, 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 that one is A, that one is A, and that one is A. Wunderbar. Great. And now this bit in the middle, let's call that B. Alrighty. And so now let's start off by getting the area. So green area will be, we have the white part in the middle, and then we have that A over there, that A over there, that A over there, and that A over there. So the green part, let's call it this part over here, will therefore be the bit at the top, which is 2A plus B plus the bit at the bottom, 2a. So the green part that we are after, if we simplify the maths, that's 4a plus b. Alrighty. Likewise, you can also see that now if I look at x, y, p, q, that the area of x, y, q, p will be the b part plus the 4 corners, and each corner is a. That's also 4a plus b. So we see that the green area is 4a plus b, and polygon x, y, q, p is also 4a plus b, that they are equal. So the green area is the area of polygon x, y, q, p. And it's not hard to see that x, y, q, p is yes, it is a rectangle. And do we know what the length of the rectangle is? Well, it's made out of the circles of radius 2. So that's 2 units. That's 2 units. We know the distance from P to X. If that is 2 units, that's going to be 2 units. That's going to be 2 units. That's going to be 2 units. So we know the distance from X to Y. So the area of rectangle XYQP will be px times xy, and px is 4 units, xy is going to be 2 plus 2 plus 2 plus 2, which is 8 units. And so what we have is that the area is 4 times 8, which is 32 units squared. Great. Another way you could have solved this problem is to have said, okay, that part over there I can copy and paste over there. That part over there I can copy and paste to the left. That part over there I can copy and paste over there. And that part over there I can copy and paste over there. So to help myself out here, just to get the message quite clear, I'm going to say the following. So part X I can copy and paste over there. Part Y I can copy and paste over there. Part Z I can copy and paste over there. And part W I can copy and paste over there. And so the area of the region desired is equivalent to, again, the area of rectangle XYQP. Done and dusted. We can work out each of the sides because we know that it's made up out of 6 circles of radius 2. A cute little problem, and it turns out that the answer is 32. I hope you agreed with my calculation. Great! We have 3 more problems to go. Let's see what problem 8 is about. In the circle shown, diameters A, B, and CD are perpendicular, and each of the 4 shaded regions is a semicircle. If the ratio of the shaded area to the unshaded area is S over U in simplest form, so you need to simplify the fraction. So if you get something like 6 over 9, you look for the greatest common divisor of 6 and 9. In that case, it's 3. You divide the top by 3 and the bottom by 3, so it becomes 2/3. So 6 over 9 is an unsimplified fraction. You want it simplified, which is 2 over 3. Our job is find the fraction, simplify the fraction, and then calculate S over U. Now again, in this problem, we have very limited data. So let's help ourselves out. First of all, we're dealing with circles. So let's indicate the centers. So that is the center of the big circle. And now let's indicate the centers of the little circles. So we have these 5 little points over here. Now let's say the radius of the small circle is R. So that's R, 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 that's R. So it's always good to introduce some variables to help you out. So the radius of the small circle is R, and the radius of the big circle is 2R. Okay. And you can see in this problem why they're using the notation S for shaded and U for unshaded. All right. So let's see what mathematics we can do. So we can do the shaded, which we're using variable S, will be 4 half circles. Alright, and so half circle means a half times the area of a circle, which is radius squared pi. So the shaded calculation in this case will be 2 radius squared pi. Great. Okay, so the shaded area in terms of r will be 2r squared pi. Now let's do the unshaded. Now the unshaded can be broken up into 4 disconnected regions, but let's rather do some area counting. We can see that the shaded plus the unshaded, if we put all of those regions together, we get a full circle with radius 2r. So that means if we take the area of the shaded plus the area of the unshaded, that will be a full circle with radius 2r squared pi. So 2r squared pi means 2r times 2r, which is 4 radius squared pi. And so what we have, the shaded area plus the unshaded area must be 4r squared pi. And you can already see where this is going. Earlier we calculated that the shaded part is 2r squared pi plus unshaded, which is 4r squared pi. So the unshaded will be 4r squared pi minus 2r squared pi, which is 2r squared pi. So a very interesting thing is happening in this diagram, that the shaded area and the unshaded area is the same. So they are equal. It didn't look that way, but when we do the algebra, when we do the calculation, we see that they are identical. That is a very interesting property of this shape. Great, so now let's do S over U. So S was 2r squared pi, U was 2r squared pi, and you can clearly see the numerator and denominator is the same, so we simplified, it's 1 over 1. So therefore, S is equal to 1 and U is equal to 1, and thus S plus U will be 1 plus 1, which is 2. So the answer to this problem is 2. There you go. We learned something very cool here, is that if you construct a diagram in this manner, that you will need the same amount of paint for the yellow part and the white part. Good. So that is problem 8 done. Let's have a look at problem 9. Let's read it. Let P be a point between two parallel lines L1 and L2. A is a point on line 1 and X and Y are points on line 2 as shown. Prove that the area of triangle AXP is smaller than the area of triangle AYP. So we see the word prove. Unlike problems 1 to 8, where the final answer was a numerical answer, here we have to write up a small essay of why this is so. So problems 1 to 8 is typical of the South African Maths Olympiad round 1 and 2. This one is something that you will see in the South African Maths Olympiad round 3, where you have to write up a good essay of why this is so. So these problems are typically harder because you need to defend with good language, good notation, and with good communication of why this is so. So in all possibilities, why is the area of triangle AXP less than the area of triangle AYP? So these problems are definitely problems that you need to practice to become more familiar of writing out good essays to prove why it is so. So if you're interested in training for the third round of the South African Maths Olympiad, you need to expose yourself to these kind of problems as well. All right, so to kickstart, say AX and BY intersect at point O with areas as shown. So I'm going to say the area of triangle AOP is little a, the area of triangle POX is little b, the area of triangle XOY is little c, and the area of triangle AOY is d. So you can see this is an essay type question because you need to explain to yourself and the marker what you're doing, what the variables mean, and how do you go about in solving this question. Okay, so by doing this, we are already have a handle on the area of triangle AXP. So looking in this diagram, the area of triangle AXP will therefore be A plus B. And can you see what the area of triangle AYP will be? The area of triangle AYP will therefore be A plus D. So our goal is to show that the area of triangle AXP is less than the area of triangle AYP. So we want to show that A plus B is less than A plus D. So they have A in common. So we are aiming to show that B is less than D. All right. So this is what we're aiming to show is why is B less than D? Because if we can achieve that, we can add A to both sides and we get that A plus B is less than A plus D. And we know that A plus B corresponds to the area of triangle AXP. And we know that A plus D corresponds to the area of triangle AYP. So using algebra, we get an advantage because now we at least get to play with areas. As you know, that's the topic of this video. Great. Okay, so we need to think a little bit more. So looking at this diagram, what do we know? We know by rereading the problem that P is a point between the two parallel lines L1 and L2. Knowing that P is a point between the two parallel lines, what useful thing can we focus on regarding areas? Think about it a little bit, okay? So P is between the two parallel lines. We know we want to prove something about areas, so we got to be thinking in terms of areas. So we going to be looking at shapes that can be useful in helping us to do this. Well, the thing here is to focus on triangle PXY. Focusing on triangle PXY, we know that its area is going to be a half base. So let's use the base XY times its vertical height. Let's call that vertical height. And as indicated in this diagram, H1. Now, P is between the two vertical lines. So let's say the distance between the two vertical lines is H. So H1 is less than H because point P is between the two vertical lines. So if H1 is less than H, that means that a half times XY times H1 is less than a half XY times H as shown in the diagram. And now let's interpret what is a half XY times H. So a half XY, so XY would be a base, and then H would be a vertical height, and it represents the area of which triangle? Yes, can you see it? Yeah, it will be the area of triangle AXY. So knowing that point P is between the parallel lines L1 and L2, we know that the area of triangle PXY has got to be less than the area of triangle AXY. Now, in terms of the variables, do we know PXY? Yes. Triangle PXY will be B plus C, and the area of triangle AXY, that will be C plus D. And now let's subtract C from both sides. If B plus C is less than C plus D, we conclude that B is less than D. And as we mentioned earlier, then the trick is to add A to both sides. So we know that A plus B is less than A plus D. And now looking at the diagram, what is A plus B? Yep, that is the area of triangle ABX. And what is A plus D? That is the area of triangle AYP, as wanted. And there we go. We have written up a little essay of why the area of triangle AXB must be smaller than the area of triangle AYP. So these kind of problems are not as easy as problems 1 to 8, where you are looking for a numerical answer at the end of the day. Here you are looking for an essay to demonstrate, to prove why it happens. So even though we did not know the values of A, B, C and D, but by the properties of this diagram, especially knowing that point P is between the two parallel lines, we were able to show why the area of AXP is less than the area of AYP. So a neat little problem, a neat little proof of why it is so. If you think you understand it, get a friend and re-explain it to a friend. And as I mentioned before, if you are planning to write the South African Maths Olympiad Round 3, these are the kind of problems you need to expose yourself and practice being able to write up good solutions. Alrighty, 9 down. Let's look at the final problem. Problem 10. Again, it's a numerical question, so not like problem 9, we just have to calculate something. But first, let's read the problem. The diagram shows two overlapping circles, A and B. The area of the shaded region is 65 square meters, while the overlapping area is 15 square meters. The area of circle A to the area of circle B is 3 to 2. By how many square meters is circle A larger than circle B? So this problem can be solved in many ways, and I am going to solve this in 2 ways. So buckle up, and I hope you've tried it so you can compare answers. It's better to compare answers than just to look at the solution immediately. Alright, so here is one way to solving the problem. So again, I am going to do area counting. So I am going to say, let the area of circle A be X. So if the overlapping area is 15, then for the area of circle A to have a total of X, then this part has got to be X minus 15. We are told that the total is 65. So the area of A plus the bit over here, let's call this bit over here Y, it's got to be 65. And if the area of A is X, so X plus Y is 65, that tells us that Y has got to be 65 minus X. So then this bit will be 65 minus X. You can always do your counting. Is the data satisfied? Yes. The overlapping area is 15. The total is 65 and the area of A is X. Great. And so now, what can we do now? So we know that the area of A to the area of B is 3 to 2. So let's fill that in. The area of A divided by the area of B has got to be 3 to 2. So the area of A, we decided to call it X, and the area of B is going to be the overlapping part plus a non-overlapping part. So that's 15 plus 65 minus X. That's going to be 3 over 2. And so what we have now is that X over 80 minus X is going to be 3 over 2. And how do we solve this? We cross multiply. If we cross multiply, we get 2x is equal to 3 times 80 minus x. So we get 2x is equal to 240 minus 3x. Getting the x's by itself, we get 5x is equal to 240. So x is equal to 240 over 5. One trick to do this calculation is to double the top and the bottom. So x is the following. It's 480 divided by 10. Dividing by 10 is easier than dividing by 5. 480 divided by 10, that means that x is 48. And now we're in business, because now we know that the area of A minus the area of B will be the area of A, which is 48, minus the area of B, and the area of B we said earlier is 15 plus 65 minus x, which is 80 minus x. So that will be 48 minus 80 minus 48. And what is this? This is 48 minus 80 minus 48, that is 32. 48 minus 32 gives you an answer of 60. So by how many square meters is circle A larger than circle B? And the answer to this problem is 16 square meters. So that is one way of solving this problem. But another way you could have solved this problem is, and we did this in an earlier problem, is by using another set of variables. Okay, so I want to demonstrate this because there is not a golden way of solving problems. It boils down into, are you doing the right mathematics, and are you able to explain what you are doing quite well? So another way of solving this problem is the following, by saying we know that the area of circle A to the area of circle B is 3 to 1. So say the area of circle A is 3x units, and the area of circle B is 2x units. Okay, now we are told that the overlapping part is 15. So by doing some area counting, if the area of B is 2x and the overlapping part is 2x, then the non-overlapping part has got to be 2x minus 15. Likewise, if the area of A is 3x units and the overlapping part is 15, then the non-overlapping part has got to be 3x minus 15. Great. And now we can focus on this other part, which says the area of the shaded region is 65. So therefore, the part on the left plus the overlapping part plus the part on the right, those three parts should add up to 65. Now the advantage of this approach is that you do not have a fraction to solve. Okay, you just have a single equation and we have to solve for x. Alright, let's quickly just simplify the left. So the 3x plus the 2x, that becomes 5x. Minus 15 plus 15 is 0. So we have 5x minus 15 is equal to 65. That is what this turns into. So we have that 5x, taking that to the other side, is 65 plus 15. 65 plus 15, you don't need a calculator. You get 80. So x is equal to 80 divided by 5. You can use my earlier trick. Double the top, double the bottom. So we double the top, double the bottom. 80 times 5 is 160. 5 times 2 is 10. 160 divided by 10. So x is equal to 60. Now, always make sure you answer what they're looking for. They want to know by how many square meters is circle A larger than circle B. So what we want is the area of A minus the area of B. So the area of A is 3x, the area of B is 2x, so we're looking for 3x minus 2x, which is x, but we just solve for x. X is equal to 16, and so the answer to this problem is 16 square meters. Done and dusted. As easy as that. So you could see, like some previous problems, we solved this problem in two ways. One approach, we ended up with a fraction. This approach, we ended up with a non-fraction. But at the end of the day, Both approaches gave us the same final answer. The in-between calculations were slightly different, but the final answer, when the dust settles, was that circle A is 16 square meters larger than circle B. So especially in Olympiad problems, you have the freedom to solve problems in multiple ways, but if it's a numerical problem, at the end of the day, you will get the same numerical value. All right, so this is the second video on areas. So you saw how much fun it is playing with area problems, especially circles, parallelograms, trapeziums, and even if you have a complicated diagram with lots of triangles and CVNs, the fun things that you can do. I trust this video gave you more confidence to enjoy Olympiad geometry problems, especially area problems. Obviously, there are so much more to explore about area problems, and I urge you to get the copy of that textbook and try out the other area problems. So I hope you learned a lot, and I hope that you are more confident tackling area problems that you are going to see at school and at Olympiads. And please, whenever you can, don't just memorize a theorem. Make sure you know how it's proven, or a small derivation of how a specific area came about. It just gives you a deeper appreciation and a deeper understanding of geometry, or in general mathematics. Thank you for watching this video, and enjoy the rest of your day. Bye.